Saxon's Trig, Lesson 92, is about probability of either and notations for permutations and combinations, which obviously we have already discussed. So probability of either begins with a highlighted words, mutually exclusive events. So we're saying if I toss a coin and it comes up heads, it can't come up tails. You cannot get both answers simultaneously. So it's a mutually exclusive event. You can't get the other part. So when we have done probability before, we've said, what's the probability of getting a blue marble out of the bag? Well, maybe there were 2 blue marbles and there were 5 in the bag, so 2/5. But now we're going to be encountering questions such as, what is the probability it is either a red or a blue? Okay, so to explain things here, I'm going to move into set notation. So we're looking for the probability of getting a red or a blue. And the way we do that is by finding the probability of it being red, and we combine that with the answer for the probability of getting a blue. Is it possible to get a red and a blue? No. So these are independent events. I'm doing one draw, but I need to check for 2 different outcomes and combine them. Now before, we took these individual events and we multiplied them together to get one answer, but we were doing independent events of multiple draws. This is talking about getting multiple things from one draw. Now we're going to be adding those probabilities together. And the symbol that we use for plus is the probability of getting an R union with the B. So there is the union symbol, which I put the U, I didn't mean to, it's a U symbol without the tab. And then there's the upside down U symbol, which stands for intersection of. And so we'll come to that. Well, I guess that is the very next thing. So this is the way to write probability of red plus probability of blue is red union with the blue. Now, if we're going to talk about intersections, they do this in a Venn diagram to show you what they're talking about. So we would have a circle of reds and a circle of blues, and well, they switched gears. They talked about boys and redheads in their Venn diagram. So boys and redheads, it'll still work. All right, so if you have, and they had in here 6 redheads. And so 2 of them landed in the fact that they were boys and redheads, and there were 4 boys. So there are 2 extra boys not part of also being redhead. And then you can randomly put some other dots around places, and they were showing that there are 4 dots that aren't boys or redheads. So they're probably the girls in the group setting. So the intersection part for the redheads and the boys would be 2 out of whatever, and here's the symbol for it. Let's jump to example. Oh, wait a minute. No, before I do that. Okay. If this is what you're dealing with, you are going to have a probability of redheads unioned with boys, which meant you had the probability of redheads plus the probability of boys, but you had a shared overlaps. With reds and blues, I don't have any shared overlaps. So when this happens, I have to minus out how many, because I don't want to double count them. I want to minus out the probability of the reds intersecting. Oh, I did that as an A. Intersecting, I just want the U, not that. Redheads intersecting with the boys. So sometimes I have to, when I add my things, look to see, do I have an overlap of these 2 items, and make sure to subtract that out. Now let's jump to example 1. A card is drawn from a deck. What is the probability that the card is an ace or a black? So how many aces are in the deck? Well, there's 1 in each of the sets. So there's 4 out of 52 cards. Plus, and it wants that combined with blacks. Now, half the deck is black. But do I have any black aces? Yes, I do. How many of those do I have? 2 out of 52. So I have to subtract out whatever overlap I have to get the correct probability. Now, to do this, I should take this back to actually 52 and 26 cards. So it might have been easier just to write it that way in the beginning. But 26 plus 4, 30 minus 2. What did I just say? Oh, 30. 30 minus 2. 28 over 52. And does that reduce? Well, most definitely down by 4. So that gives me 7 and 13. Yep. So 7/13 is that probability. Now, example 2. An urn contains 4 whites, 3 blacks. 4 white, 3 black. 2 of the white balls are rough. So 2 are rough. And 1 of the black balls is rough. What is the probability of drawing a ball that is either rough or white? So rough first. How many roughs do I have? 3 out of how many are there all together? 7 plus, what's the other thing it wants? White. How many whites? 4 whites out of how many? 7. Do I have any overlapping rough whites? Yep, 2 of them. So I need to subtract off 2 sevenths. So 4, 5, 6, 7, back down. 5 sevenths is the probability of those 2 together. Now, all right, out of space. Okay. Part B, notations for permutations and combinations. You have already been given these formulas. So basically, you're going to take this as a review. So probability of n items pulling r of them gives you the formula n factorial over the subtraction of n minus r factorial. For combination, again, n items pulling r, you have the same n factorial over and the same subtraction of n minus r factorial, but combinations don't care about order, so they have the extra n factorial divided back off. Just a second. Not n factorial, r factorial. I knew that didn't sound right. R, because that's the number I'm choosing. R factorial, get rid of that order. Now, example 3. Take the permutations and combinations of 7 things taken 3 at a time to do a concrete development for those formulas. So again, they're going through just proving that these formulas work. We've already done it, so whatever. So permutation of 7 items pulled 3 at a time. Okay, so instead of doing the formula, to prove it, we are going to say we need 3 blanks. How many choices for the first one? 7, 6, and 5. So what do I not need? 4, 3, 2, and 1. How do I get 4? 7 minus 3. So 7 factorial would have been 7, 6, 5, 4, 3, 2, 1. Killing off 4, 3, 2, 1. There's our answer. We've proven that the formula works. Okay, so now the same thing for combination. Again, I have 3 items, but they're not necessarily in a line. They could be in a circle, or it just doesn't matter what the order is of these lines. So we have 7, 6, and 5. We've still lost the same 4, 3, 2, 1 because we don't need it. There's that part. But I don't care about the order of these 3 items. So I'm going to lose 3. How many combinations of 3 items do I have? 3 times 2 times 1. So we have to divide those out as well. 3 and 2 kills off a 6. And there I've just proven the 2 formulas.